Hello everyone. So today we'll talk about a very famous problem in quantum mechanics or a quantum mechanical system. There is the infinite square well. So the idea is we have a well which has a width between 0 and a. So x is between 0 and a, and inside the well the potential is 0, and outside of the well the potential is infinite. So we have these boundary conditions which are 0 if x is greater than 0 and less than a, and it's infinite otherwise. So it is 0 or and x is greater than or equal to a. So this is the boundary condition, and the the wave function is. So now we will solve the Schrödinger equation to find the stationary solutions for the system. So inside the potential is 0, so we will write the Schrödinger equation as d2 psi divided by dx squared is equal to minus 2m e over h bar square psi plus v of psi. So this is the Schrödinger equation, and since our system is the inside the well the potential is 0, so these are the initial conditions we are going to use. And okay, so inside v is equals to 0, so the Schrödinger equation reduced to d2 psi divided by dx squared is equals to minus 2 e by h bar square psi. So this is a second order differential equation. So we will simplify the equation by changing the variable. So we will introduce a new variable k squared that is defined as 2me over h bar squared. So the energy is given by E is equals to h bar squared k squared divided by 2m. So then the equation is written by like this, minus k squared psi. So this is a second order differential equation. We can solve it by using any method that is used in elementary differential equation course. So the solution is given by this: psi of x is equals to c1 cos of kx plus c2 sine of kx. So here the important things are these constants. So we will find the value of these constants by using our initial conditions. So those are given to us here. So the first condition is initial. From step 1 till here it was all math. Now we will introduce physics, and physics come into the picture through the initial conditions. So the first initial condition is psi is 0 at x is equals to 0. Okay, so if I put psi of x is equals to 0 is equals to c1 cos of k of 0 plus c2 sine of k of 0 is equals to 0. So here c1 cosine of 0 is equal to 0. So cosine is 1, cosine of 0 is 1, so c1 is equals to 0. That come from the first initial condition. So c1 is 0, and then we are left with psi of x is equals to c2 sine of kx. So here we apply our second initial condition, and that is psi of a, when psi of x is equals to a, is 0. So psi of a is equals to c2 sine of ka is equal to 0. It means c2 sine of ka equal to 0. So this sine of ka can be 0, like we can make this expression 0 if we make the angle 0 or angle pi, okay, multiple of pi. So ka is equals to n pi. If ka equals to n pi, then for all the values of n, this initial condition will be satisfied. So it means here we have for every value of n we have different value of k. So kn is equals to n pi by a. So putting everything together, we will write psi of n x is equals to n sine of n pi over a x. So this is the solution of the Schrödinger equation for the infinite square well. So we have an infinite square well that is given over here. I will just copy this cartoon down to the part where I need it, and let increase the size a bit. Okay, so here, so now we have the solution, and this is the normalization constant, and we need to find the value of normalization constant. So normalization we usually do from when psi into psi star dx is equals to 1, when we put like the the probability of finding the particle, or finding the probability of finding the particle within these limits equals to, like, it's 1 is the maximum. So if I put everything here, so n squared 0 to a, these are the boundaries, so sine squared n pi by a dx is equals to n squared by 2 dot a, which implies that n is equals to 2 by a squared root. So sine n of x is equals to 2 by a square root sine of n pi by a x. So now for every value of n, we have a different wave. So for example, for n is equals to 1, let me do it in greens. For n is equal to 1, we have psi of 1 of x is equals to 2 by a sine of pi by a x. So this is for 1, for n is equal to 1. So here one more thing I would like to write here is the energy. E n is equals to h bar square k n square divided by 2m, so which implies that h bar square pi square n square divided by 2m a square. So E1, the corresponding energy, E1 is equal to h bar square pi square divided by 2m a square. So if I take this center as the mean, then for n equal to 1, the wave would be like this one. It will be a semicircular wave. For n is equals to 2, if I put psi of 2 x is equals to 2 by a sine of 2 pi over a x, and E2 is equals to h bar square 4 divided by 2 pi square ma square. This is the energy, and the shape of the energy level will be like this. So it is n is equals to 2, so there is 1. And for psi of 3 is equals to 2 by a square root sine of pi 3 pi by a x, so E3 is equals to 9 h bar square pi square divided by 2 ma square. It will be like this. So here, and no, it will be like this. So here and here we have 3 nodes. So this is the solution of infinite square well, and we can also find there are many similar systems like finite square well and harmonic oscillator in quantum mechanics. We will solve them in our upcoming lessons. So thank you.